So what I want to do in this video is get a little bit familiar with the idea of molecular mass. And let's start off with a molecule that we're all quite familiar with. In fact, we are made up of this molecule, or to a large degree made up of this molecule, and that is water. And the molecular formula for water is H2O. H2O. Every water molecule has 2 hydrogen atoms and 1 oxygen atom. And what I'm curious about is, well, what is the mass of a molecule of water? And so the way that you might think about doing that is, so, well, what's the mass of each of the hydrogens? And you're going to have 2 of those. And then what's the mass of the oxygen? And that would be a reasonable way to do it. So what is a mass of the hydrogen? A hydrogen has a mass, and we can go to a periodic table here. So I've got one right over here. And you see hydrogen, it has its atomic number 1. That's the number of protons. That's what makes it hydrogen. And then down here you have this number. I think you can see it's a little bit small probably on your screen. It says 1.0079. This right over here is the atomic weight of hydrogen. This is if you take the various isotopes of hydrogen on the planet Earth, and you take the weighted average. So the ones that are more common, they're weighted higher. The weighted average of their atomic masses is 1.0079. Now, for the sake of this first pass, we're just going to say, well, it's a roughly 1 atomic mass unit. And one way to think about it, and this isn't precise, and it's not how things are defined, but it is a useful way to think about atomic mass, or mass on the atomic scale, is that 1 neutron or 1 proton have an atomic mass of approximately 1 atomic mass unit. In other videos, we'll talk about why it's not defined this way and why it's based on the carbon-12 isotope and all of that. But this is a fairly useful thing that is helpful to think about, okay, what is the atomic mass likely to be, or what is it roughly? And so when you see that hydrogen, it has 1 proton, clearly, that's what makes it hydrogen, but it also has an atomic mass of 1 that says, hey, or roughly 1. It says, well, it must not have it must not have a neutron. And that is the case. The most common isotope of hydrogen on Earth is just a proton with an electron. And the electron also does contribute to mass, but it's negligible compared to the proton. So most of this mass, or this mass, is essentially the proton, a little bit of the electron, and also kind of the weighted average when you think about the other isotopes of hydrogen that maybe might have a neutron that is involved with it. But for the sake of this, we could say, hey, hydrogen, it's a proton with an electron kind of buzzing around it. And so it is approximately 1 atomic mass unit. And then oxygen. Oxygen, same idea. We'll look at the periodic table. You could guess what its mass is close to. Oxygen, the most typical isotope of oxygen that you'll see on Earth, has 8 protons. The 8 protons are what makes it oxygen. Any oxygen has to have 8 protons anywhere that you are in the universe. If it doesn't have 8 protons, it's not oxygen. But it's going to have 8 protons. It's going to have 8 neutrons. That's the most typical isotope of oxygen. And so you might guess that its atomic mass is 16 atomic mass units. And you can see that your guess is pretty good. When we look at our atomic weight right over here, which is the weighted average of the various isotopes of oxygen as found on Earth, you get 15.999, which is pretty close to 16. So our approximation to 16 is pretty good. So then based on these numbers, you would say that this H2O has an atomic mass of approximately, well, 2 from the hydrogens. And where did I get the 2 from? Each of these 2 hydrogens have an atomic mass of 1. So you're going to have, if you have 2 times 1, it's just going to be 2 atomic mass units. And then 16 from the oxygen. 2 plus 16, which is going to give us 18 atomic, let me do this in another color since I've been using, it's going to give us 18 atomic mass units. Now, if you wanted to be more precise, or if you wanted to say, well, I have this big bag of water, I'm not looking exactly at 1 water molecule, what is going to be on average the mass of those water molecules, then it might be helpful to get a little bit more precise. Then it is helpful, especially if you're talking about a large number of molecules and you really just want to take the weighted average of all of those molecules, then it makes sense to say, well, let's use the atomic weight. So for hydrogen, The atomic weight was 1.0079, which is once again 1.0079 atomic mass units. So we call it atomic weight, but it's really just the weighted average. It's not weight in the kind of the physics sense of measuring a force. So 1.0079 atomic mass units, and the oxygen is 15.999 atomic mass units. And so if you wanted to get a more precise number here, let's get a calculator out. So if I get my calculator, so I'm going to have 2 times 1.0079 is equal to, and then to that I'm going to add, so plus 15.999 gets us to, and let's see, I should go no more than 3 decimal places to the right if I want to care, since I added this. So if I don't want to kind of add precision here, so let's see, I'll go, if you want a review of that, you should look at the video on significant figures. But since I added something with just 3 decimals to the right, I shouldn't have more than 3 decimals in my answer. So 18.01, I'll round in the thousands place, 015. So 18, so the real one is 18.015 atomic mass units. And you could actually consider this the molecular weight, because we're using atomic weights. We're using weighted average. And you could think of, well, maybe the weighted average of water molecules would be a little bit closer to this. But these two numbers are very, 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 very close. And so we might call this molecular weight. But either way, these ideas are very, very closely related. And when we're thinking on the atomic scale, when people use the word weight, they're not using it like a force like you use in physics that you would measure in newtons or pounds. They are essentially taking a weighted average of masses. So the molecular weight of water, 18.015 atomic mass units. If you wanted to just kind of be a little bit loosey-goosey, you could say it's roughly 18 atomic mass units.